Okay, so last time, right, we learned some new words, one-to-one injective, onto surjective, and bijective. And then we saw how to prove something's one-to-one and onto, okay, right? It's a bijection. And the key with one-to-one, just to remind you, was to assume you had two things where the function was equal, and then work to show, oh, I actually had A equal B in the first place. And the key with onto was this kind of magic behind the scenes where you work and work and work until you get some magic domain element that outputs the range element you want. Okay. All right. So that's what we did last time. So there's one more idea we need for this section, major idea. It's to talk about inverse functions, right? And you've seen these, you've heard of these before. I mean, you've been told e to the x and natural log are inverses, right? Sine x, when you were in Cal 2, you did sine inverse of x. So you've seen these, but let's get the technical definition. So if R is a subset of A cross B, then our inverse is the set of all B comma A such that A comma B is an element of R. All right, so let's do a little example here. We'll make a really short one. So if R is, I don't know, 1, 1, 2, 3, and 4, 3, what is our inverse going to be? 1, 1, 3, 2, 3, 4. Okay. This is actually what you did when you talked about inverse functions, right? You switched the x and the y, okay? So you switch the input and output. That's all we're doing. So with these relations, do either of these or both of these or one of these, whatever, qualify as a function? So assuming you're covering the whole domain, but is R a function? R is a function because given an input 1, 2, or 4, you know exactly what to output, right? What about R inverse? No, that 3 messes it up, right? If I give you a 3, you go, oh, I can output 2 or 4, right? So what will it take for R inverse to be a function? Well, so yeah, so I'm not allowed this type situation. We have a word. One of our words we learned last time, one-to-one. Injective excludes that, right? One-to-one is where you plug in something, he has his own special thing nobody else gets, right? So when is our inverse a function? When R is 1-to-1. Yeah, that is the exact same thing you learned back in, I don't know, algebra, pre-calculus, calculus. So it's still true. That's good. All right, we didn't break math. Now, one thing to be careful about, technically, you could argue you want R to be onto, because then when I flip it, I've used my whole domain. But if it's not onto, we just limit it down, right? So like with sine, we say, okay, yeah, it's not onto the real numbers, but it's onto -1-to-1. So we can just limit that codomain down to what we need. Okay, so we don't worry as much about onto. 1-to-1 though, we gotta have that. Correct. So, and actually, That's our example A here, yeah. So for each of the following, find the inverse function if it exists. So sine as is, it's not 1-to-1, right? So technically there is no inverse function if I view sine. So let's look at A. So here our function is going, if I view sine as going from R, even if I view it going into -1, 1, so it's onto, it still doesn't work, right? Because it's not 1-to-1. But if I restrict it down to, what do we do? -pi/2 to pi/2, then it is 1-to-1. Yes. So that's not L, that's a straight line with the set I'm restricting it to at the bottom. We, I think, saw that for about 5 seconds last class. Maybe. Oh, maybe that was in topology. So, but yeah, that's what that notation means. That line, sorry, straight line with the set at the bottom means I'm only using this as my domain. Okay. So that's what we have to do in calculus 2 to get sine inverse to be an actual function. Okay. For the purposes of this section, right, it's just going to say, is this 1-to-1 or does this have an inverse? It's not going to say restrict it so that it does. So our answer to this would just be like, nope, not 1-to-1, no inverse. Done. Okay. All right. What about B? Why do you say no? Yeah, we did already say this is not 1-to-1. Give me an example of two things that are different inputs but have the same output. Yeah, absolutely. -1 and 1 have the same output. So yep, so not 1-to-1, so it doesn't have an inverse. Okay. All right. Now C, what do you say? Yeah, some of you are remembering to flip back and look. Yeah, we did say C was 1-to-1. So I'm gonna come down here. How do we find the inverse? Well, what did your high school teacher tell you to do? Swap X and Y. Okay. And that makes sense, right? Because what does our inverse relation say? It says you swap your coordinates. So we just swapped our coordinates. All right. So you'll notice this is actually the same work we did when we were looking to see if it was onto. Okay, it's actually the same steps. So there we go. There's my inverse function, is the cube root of the whole quantity x minus 5/2. Now that inverse function, well, so C, we can say this, the original goes from all reals into all reals. So what's that mean about the inverse? Same thing, right? They just flip, but you still get all reals into all reals. Okay. All right. Let's look at D. What about D? It has a hole in it, but is it 1-to-1? Yes. So it does have an inverse, but because of that hole, you're right. My domain is the reals take away -1, right? I can't have -1. And that got mapped into, what was it? The reals take away -2, I believe, is where the hole falls on the y-axis. Okay. So when I take his inverse, that should switch. Let's see. Okay. So we have y, well, that's the original. So let me switch. X equals y squared minus 1 over y plus 1. Use algebra. X equals y minus 1. So y equals x plus 1. Unless I did something funny, that's what I'm getting. Check my algebra. All right. So that's my inverse function, but his domain, technically I'm not allowed to plug in -2. Inverse. Well, if I plug -2 into that inverse function, what would it output? If you plug in -2 here, what would it output? -1, which is what I wasn't allowed. So my domain and range did flip. You see that? Okay. Because I'm not allowed -1 in the original domain. Your homework problem related to this, your domain is something like that, where you're missing one number. But I don't think your function simplifies. I think your function is something like x over x plus 1 or whatever. And so it leaves out -1. So you have to be very careful that you're never using -1 for that function, right? Okay, just a comment. All right. E, what about E? Is that going to have an inverse? Yeah, lines are very much 1-to-1 unless, what? Well, the whole was okay, but what? Yeah, so if m equals 0, no inverse. Right, and that makes sense, because if m equals 0, my equation becomes y equals just some number b. How am I going to take an inverse of that? That doesn't make sense, right? There's no y and x to flip here. But in most cases, we have our slope not equal to 0. Then yes, it is 1-to-1. We can get an inverse. Well, let's see. Swap your x and your y. So we get x minus b equals m times y. X minus b divided by m equals y. And if we had jumped straight into finding the inverse, what would jump out at you at that last step that we have to be super careful about? M can't be 0. So that helps justify what we said, right? You cannot divide by 0. This cannot be a horizontal line. Okay, but a horizontal line is not 1-to-1 in the first place. So if a question just says find the inverse function, this is what it wants you to do. Now, we can check our answer with a fact from high school. How do you in high school tell if two functions are inverses? Okay, so from high school, if you have f and f inverse and you compose them, you get x. And it has to work both directions. Okay. So that's one way to check your answer. Let's do that with this last one because that's the easiest one. So we had our f of x is mx plus b. Our f inverse is x minus b divided by m. So let's try. We'll just do one direction. It's just algebra. Plug the inverse into the original. We get m times x minus b over m plus b. Well, what happens? M cancels, and then what happens? 3. Yep. So we get x. Okay. Because the m's balanced to 1, then the b's balanced to 0, leaving me with just x. All right. And same thing if you did the other direction. Okay. So this, when we get plain old x, it has a special name. It's called the identity function. And this is actually rather important in upper level math. This comes up a lot. The function that basically sends a thing to itself. It's called the identity function because everything gets to keep its own identity, right? It doesn't change them. The reason this is important is the same reason a simple number like 0 is important, right? Because I can add 0 without changing things. All right, so the identity function is going to play that type of role for functions like 0 does for numbers. Okay, so what we just said then, well, there's the definition of composition. We'll do that in a second, but two functions are inverses if and only if f composed with f inverse of x equals, and now we'll say the identity function, okay? And then we'll do the other direction. F inverse composed with f of x equals the identity function. So we could have put an equals x. I'm just trying to use the notation to bring that in. Because what I'm saying here now is these two sets are equal because our functions are really relations, which are sets of ordered pairs. So when I compose, so that's going to tie into this. When I compose two functions, I'm really getting a set of ordered pairs that deal with input and output. So we're saying that those sets are equal. The set created by the composition is the same thing as the set created by the identity. Yeah. Yep. You guys remember how composition works with functions? You guys okay with that? Okay.
Like basic math? No.
No. Okay. All right. So here we have this definition, but let me kind of expand on it. I guess you can fit it off to the side over here. So we have F going from A to B, right? G going from B to C. So let's think of this. Well, let's think of it as a function, and we'll think of it as a relation. So if I compose them, right, that means I take F and I plug G in first. Whatever the heck G outputs gets plugged into F. Now let's make sure that makes sense with the way our functions are defined. Oh, nope, I did that backwards. It should be G composed with F. Why doesn't this make sense with the way it's defined? When I plug in G, I plug in something in B, and what's it output something in? C, which is not allowed for F. So, all right, backwards. Oops. So, exactly. So, you have to be very careful about the order of composition. So remember, adding and multiplying order doesn't matter, right? But composing, it very much matters. Yeah, so, all right. So now F, I plug in something from A, it outputs something from B. That something from B is plugged into G, which then outputs something from C. Okay, you guys see that's how composition is working. Up to now, you know, in algebra and calculus, when you did this, it was pretty much real numbers, right? You plug in a real number, it outputs a real number. So you plug in a real number and output a real number. Here in upper level math, your set might not be numbers. It could be letters A, B, C, right? And you could just say, okay, F sends A to 3 and B to 5. And so your composition, you have to be very careful about your sets as to what's being inputted, what's being outputted and plugged in, okay? So in terms of sets, we could write it this way. G composed with F equals the set of ordered pairs. Let's see, I input something from A, so I'm going to use little a, output something from C at the very end. C, such that, all right, there exists a B in capital B. Here we go, we have AB, well, let's use function notation. F of A equals B, and G of B equals C. So does that make sense? It's kind of like transitive, right? It's kind of like it's collapsing down that middle in a weird kind of way. It's not transitive because I'm dealing with two different relations there, not one relation twice, but it's a similar idea of that middle collapsing, okay? And if we had time, we'd do more with inverses, but for our purposes, you know, you just need to be able to find it, and this is a good way to check, okay, that composition works. All right. Any questions on that? Okay, so when you're dealing with proofs for functions, you can treat it like a function like we're used to, but if you're getting stuck, chances are it'll be easier if you think of it as a set of ordered pairs, because we know how to prove things with sets. Okay, so if you think of it as a set of ordered pairs, you can work with that. So, but like I said, there's only, with this homework, you shouldn't have too much, just because we're running out of time. So, yeah. But now, so good. We have a little bit of time. I want to show you something that I'm not going to test you on, but it is kind of important to math. So we've been talking about bijections. And in math, there's this idea of different types of infinity that actually becomes kind of important, right? So if I take the natural numbers, you know, the integers, the rational numbers, the real numbers, these are all infinite sets, okay? Which ones to you seem like they're kind of the same type of infinity? Okay, natural and integers, those seem kind of the same. So, well, rational and reals, kind of yes, kind of no, right? Yeah, so the reals include all those irrational numbers and the rational and the whole. It ends up being, the rational numbers are actually the same type of infinity as the natural numbers. That's crazy when you think of it visually, because on the number line, the natural numbers and the integers are just separate dots, right? But the rational numbers would be dots throughout this whole space. And yet they're the same type of infinity, but the reals are different. So let me show you, just give you a gist of how mathematicians come to this. So the idea is, so we say cardinality of A equals cardinality of B if there exists F from A to B that is a bijection. Okay, so it has to be 1 to 1 and on 2. Now, for to show that this makes sense, I'm going to go back actually to page 1 of our notes. And let's look at the first one in the first row and the first one in the second row. So both these are 1-to-1, but only the second one was on 2. You see that? This guy was not on 2, okay, because it missed the 2. But this guy was 1-to-1 and on 2. Notice they both had 4 things in them. And that makes sense. If you're going to be 1-to-1 and on 2, if you have 4 things, you need 4 things to go to, right? If you have 10 things, you need 10 things to go to. So with finite numbers, this definition makes perfect sense. So what Cantor did, very, very smart man, he extended this to describe infinities. Okay, said, well, if I can get that same relationship between infinities, then they're the same type of infinity. Now, mathematicians at first flipped out and said, you can't have different types of infinity, that's crazy, da, 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 and he got a lot of pushback, but this is now foundational to mathematics. All right. So here's how you can show the natural numbers and the integers have the same. So let's put, well, how do I want to do this? Okay, so let's put the natural numbers, kind of just a list going down, blah, 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 blah. What I'm going to do with the integers, I'm going to take the integers and fold them in half at 0 and interlace them. So I get like 0, 1, -1, 2, -2, 3, -3. So you guys see what I mean, that I folded them in half and interlaced them? Well, so this function, here's my function, okay? And I could make up a piecewise function that describes this, but this is the function. Will I ever repeat an output if I continue this pattern? No, right? Will I cover all the integers? So will it be onto all the integers? Yeah, if you say, well, I want you to output 1,000,000, well, I just go down my list. It looks like it'll be at 2,000,000. We'll output 1,000,000, right? And 2,000,001 will output -1,000,000. So yeah, this is 1-to-1 and onto. We have a bijection from the integers, well, from the natural numbers to the integers. So these are the same. So let me show you, because it's really, really smart. Cantor came up with this, how you can get from the rationals to the natural numbers, or naturals to rationals. So we got to make a little chart here of our rational numbers. So first, we'll just do positives. I'm going to do denominator 1, ... Then we'll do denominator 2. And what do you think is next?
3.
Denominator 3. Yep. I'll just write in one more row, but obviously you could go forever. Okay. So here I have my positive rational numbers. Okay, the next thing we do is get rid of repeats. So like 2/2, 3/3, 4/4, those are repeats of 1. What other repeats do I have here? 2/4 is a repeat of 1/2. Anything else that simplifies? 4/2 is a repeat of 2. I think that's it. But you'd have repeats all the way through, right? So then here's what Cantor did. He said, okay, I'm going to put these into a single list. I'm going to start with this diagonal, take the number 1. So 1 gets sent to 1. Then I'm going to take this diagonal. So 2 gets sent to 2, but 3 gets sent to 1/2, because that's my third rational I came across. Then I take the next diagonal. 4 gets sent to 3. 5 gets sent to 1/3, because I skip over the repeat. And then you can just do this the whole way through, and you will get a single list, right? So you guys see what I mean? If I were to take these, well, I can do that and write them out. I would get 1, 2, a half, 3, 1/3, 4, 3 halves, 2/3, 1/4, on and on and on. Okay. So these are just listing whichever rational number I came to on the diagonal I'm on. And there is no nice formula or pattern you can make. It's just taking the diagonals because the repeats mess up any nice pattern you could have. Okay, so here's our function. We send 1 to that, 2 to that, 3 to that, 4 to that. Whatever the heck is 5th thing in my list is what 5 gets sent to. Whatever the heck is 6th in my list is what 6 gets sent to, right? So will I get any repeat outputs? No, because we crossed them off. Will this cover all rational numbers, positive rationals? Yeah, this will cover all the positive rationals because you say, well, I want you to get to 13/27. Like, all right, it's going to be a big square, but I'll keep drawing until I get to 13/27, and you can list them out. Okay. So I have a 1-to-1 and 1-to-2 function. So the rationals can actually be put into a list. So they have that same type of infinity. Now we did the positive rationals, but remember the trick we did for the integers? I could do the same trick now, is throw in 0 and the negatives and interlace them, and I still got a single list. So it's ridiculous list, but it's a list. You guys see what I'm kind of saying?
I'm kind of struggling to understand.
It's whole numbers and fractions.
Yeah, so this is my natural numbers, that's my domain. This is my rationals, that's my range. And so those whole numbers are because whole numbers are rational numbers, right? I could write it as 1/1, 2/1, 3/1 with that. Is that what's bothering you? Or is it because you're trying to find a nice formula and there is no nice formula or pattern? Yeah. Okay, yeah. So, but the idea is that I'm able to get a function. It's a ridiculous function with no nice pattern to it, but I am able to get a function. So they're the same type of infinity. So then Cantor used this same argument to show that it's impossible to get, well, it's a slightly different argument, but similar. It's impossible to get a 1-to-1 onto function to the reals like this. And basically what he did is so notice all of these, the key comes down to being able to put it in a list, right? Because then I could say first thing is what 1 is sent to. 10th thing is what 10 is sent to for my function. So what he did is he said, okay, pretend I have a list of real numbers. And he showed, oh, you left this off, put it in your list. Oh, you left this off, put it, no matter what your list is, there's always something missing. So that's what he did.
So if you have 2 lists and they're 1 and 1, 1 to 1 and 1 to 1.
Correct. Yeah, well, and that word list is automatically implying it matches the natural numbers because they create a list. With the real numbers, how are you going to even start, right? Making a list with the real numbers. You'd be like, well, I want to start with pi. It's like, okay, what am I going to put next, right? So that type of infinity is called countable because you can make a list. Okay. The reals and all other types of infinity are called uncountable.
So why wouldn't it be the same type of distance?
The reals? Or
rationals?
yeah, so the rationals are then. So this definition ends up being an equivalence relation. So once these two have the same type of infinity, if one of them matches the integers, then they both match the integers. Yeah, and that's why it's okay to use an equal sign there. So we said the natural numbers match the integers and the natural numbers match the rationals. Therefore, the integers match the rationals. Yes.
Could there be like a pattern that did the 1, 2, 3 all with numbers? So like go down to where you have put like 1 to 1, 2 to 2, and 3 to 4. Like I was counting like 1, it can't go back to the beginning of count.
Yeah, so if you try to get a pattern here, because we did like 2 a half, 3 a third, if you tried 4 a fourth, 5 a fifth, then you're leaving out anything of those forms, and you never get to them because you never finish your first pattern. So that's why we need this weird interlacing that has no pattern to it, is so that everything appears. Yeah, and like I said, it was Cantor that came up with this idea. Kind of blew people's minds when you did it. They actually got kind of mad. But yeah, so here's another unsolved problem then. Is there a type of infinity between the natural numbers infinity, which we said the integers and the rationals, that algebraic I said earlier, algebraic is still countable, okay? Transcendental, they match the real numbers actually. So the real numbers, the transcendental, the irrational, those are all the same infinity as the reals. So unsolved problem, is there a type of infinity between those two? Between the naturals type of infinity and the reals type of infinity? Yeah, we don't know. They've proven that all of our math works either way, whether there exists one in the middle or not. It's called the continuum hypothesis. If it's true, our math works. If it's false, our math still works. But yeah, it's interesting, isn't it? But there are bigger types of infinity than the reals. Take the power set of the reals, that's a bigger type of infinity. Take the power set of the reals, that's a bigger type of infinity. So it's crazy. Infinities are cool though, guys. That starts getting into my area of my dissertation where I did set theory, so I get a little excited. But anyway, math majors, those words, countable, uncountable, gonna come back in your later classes. Okay. So, any questions on that fun aside? Yep. And that is a chapter in your book. If, over the summer you feel like it, just go read that chapter.
Honestly, I think I'm gonna need to like stay on top of this stuff for the summer too. I feel like I'm barely keeping up.
Yeah, no, and this stuff, this is foundations of mathematics. It is going to come up in your later classes. It depends on the class as to which parts of it you'll need. So.